Okay, can I just welcome everybody? This is the first session for today, and actually the first session for the main conference. And on behalf of Linux Australia and LA and the sponsors, I wish you a very pleasant conference. For this first talk, we have Adrian Sutton. He's going to talk about concurrent programming with Disruptor. Adrian is a developer at LMAX, the London Multi-Asset Exchange, writing latency high performance code. And there's a little bit more about him there, but I will let him introduce himself probably better than I can do it. Okay, thanks.
Thanks, and welcome. So, as Daniel just said, my name's Adrian Sutton, and I'm from LMAX Exchange. We're a UK-based financial exchange, and as you can see from the big logo, three things we care about are speed, price, and reliability. And with exchanges, price and reliability really drive from speed. So, a year or two ago, we open-sourced what is essentially the core of our exchange, which we call the Disruptor. And today I'd really like to take you through that and talk to you about what the Disruptor is, why it's fast, and how can we and you use it most effectively. Unfortunately, it turns out that in a 45-minute talk, there's pretty much no chance of covering all of that. So what we're mostly going to focus on is how to use it most effectively. We will cover what it is and give you a bit of a background, because most people won't have heard of it, and we'll learn a bit about the why is it fast. But I would highly recommend you go and look at some of the existing talks that are out there. They've been filmed. People like Mike Barker and Martin Thompson talk about why the Disruptor is fast in great detail. There's kind of hours and hours of content on it that we just can't fit in here. And Trish G does a lot of good stuff on what the Disruptor is and how to get the very basics of it in terms of the code. So the core premise of the Disruptor is that we want to be able to pass data between threads really fast. When we first built the exchange, we tried it to be multi-threaded and process orders in parallel, and we just found there was this huge amount of contention trying to get the common state of the order book, and there wasn't really much we could do to avoid that except to go single-threaded. So our core matching engine is actually single-threaded, and it goes much, much faster that way. But we wanted to still be able to work in a concurrent fashion and have any of those surrounding jobs, journaling, marshalling, and various other tasks like that, we wanted them to happen on other threads. So we still wound up with this contention point where we're trying to get data from one thread over to the next one into that core single-threaded matching engine. And queues have this issue where they tend to contend on the head of the queue a lot. So we invented the Disruptor, and for all of the talks on it and for all the time you can spend talking about it, ultimately all it does is it passes data between threads really, really fast. The second thing it will give you, though, is a way of arranging consumers of that data. So you can have a number of threads and they can be set up in a certain sequence. And it gives you some nice happens before semantics so that you know that the event you're processing now, the consumers you've set up beforehand have already processed it. Now at its core, there's just a big ring buffer inside the Disruptor, which is our data storage. It's not a particularly new data format. It was invented many years ago. But if you're not familiar with it, a ring buffer is essentially an array that we reuse. So we start at index 0, and whether we're publishing or consuming, we just start with an index of 0 and increment it round. So we go to 1, if we're publishing, we'll put in, if we're consuming, we'll read out, 2, and so on, until we get round to the last slot. And in this really small ring buffer, that last slot is 7. The next step is we go to 8 and we overwrite 0. So we're going round and round the ring buffer with an ever-increasing sequence number. And it turns out that the ever-increasing nature of the sequence number is really useful for things like monitoring. So we expose that out via JMX, and then at any point we can see whether events are still flowing through our system, or whether we've hit an error and one of the threads has died and it's not processing events anymore, or it's gotten stuck on an event in a deadlock or something. And it can also be useful as a unique ID. So a lot of the events that go through our system, instead of having some external way of generating an ID, we just take the sequence number from the ring buffer. We know it's going to be unique within the application, and we use that and flow that through the system. Now, if we have consumers and producers running around the ring buffer as fast as they possibly can, there are a couple of restrictions we want to put in place. And that's firstly that the consumer shouldn't try and read a sequence number unless the publisher has already finished publishing to it, so the data's there to be read. And secondly, if the producer is going to wrap around and overwrite an existing entry, it needs to be sure that the consumer has already processed it. Typically, you'll find that an application will either have the producer constantly pushing up against the consumer, so the consumer is the slow side, the producer will quite quickly wrap around and be waiting on the consumer, or the opposite, the consumer will be waiting on the producer, and that's typically the way you want it. But it's quite rare and fairly unstable state for it to be somewhere in the middle, because that suggests that for a period at startup, they were out of line. You kind of half filled your ring buffer, but then they're perfectly in sync and processing at the same speed. Not very likely to happen. So that protection and that happens before semantics that I mentioned before are really done outside of the ring buffer. And it's done by sequence barriers. Now when you look in the code, you'll see that the ring buffer will create sequence barriers for you. So in a sense, the ring buffer is still doing this. But we do work quite hard to have a separation of concerns in the code, and that's one of the reasons that it's quite fast, is that each thing has its own independent job. And again, it's that reducing contention. So here you can see we've got a sequence barrier between the producer and the consumer, such that the consumer will call wait for on the sequence barrier, and that will block until the producer's sequence number has reached the number that the consumer is waiting for. So the consumer calls wait for 5. Once the producer's sequence number is at 5, then it will return and allow you to continue. And that's really the sequence barrier is effectively polling the producer in that sense. There are a number of wait strategies you can pick from, whether you want it to use actual locks or whether you want to use a CAS instruction so that you're busy spinning, and that'll give you the lowest latency, but obviously it's going to consume a core while it does it. So there are trade-offs in which wait strategy you want in terms of the performance that you need and the responsiveness you need versus the number of cores you have available. Because obviously if you have 10 consumers all using CAS and busy spin to wait on their dependencies, then you're going to need at least 10 cores, because otherwise you'll never make progress. You're too busy checking to see if it's moved on. The advantage of having sequence barriers as a fairly separate concern also means that we can start doing more complex structures. So we can have 2 consumers reading from the same ring buffer, and they will both immediately process and process in parallel the events once the publisher has made them available. So you can see they're both waiting on the same sequence barrier. And similarly, the sequence barrier preventing the producer overrunning them is waiting for both consumers to reach the expected point. So it's basically doing a min of their sequence numbers. And you follow that along, you can start building up pipelines. So here we have consumer A will process the event as soon as the producer publishes it, and then consumer B can process it, and then once B is finished, C can process it. Now notably, while this diagram makes it look like we're passing the event from one to the other, it's not a call chain like that. They are just waiting on each other and reading from the ring buffer. The data is always staying in that ring buffer. And what that means is that consumers can run ahead. So for example, consumer A might be the fastest consumer. It might be processing sequence number 10, and B is a lot slower, so it's still processing sequence number 5. That's fine. It's still, B hasn't overtaken A. That's the only thing our sequence barrier is preventing. It doesn't prevent A from running ahead and getting ahead of things. And that's especially useful in terms of dealing with bursts of data, and we'll see how you can then take advantage of batching to help your slower consumers keep up. But also it means that you can be taking full advantage of your CPUs because your earlier consumers can run ahead. And similarly, as we saw before, you can have consumers running in parallel. So here we kind of have a diamond shape where once A processes the event, both B and C can process it together if they're busy waiting on A, and then D. Now, that doesn't mean that necessarily B and C are running the same event at the same time. If they're running at different speeds and they've got a backlog to catch up on, they might actually be processing events. But if they're both waiting on A to get their next event, then as soon as A finishes, both will pick it up at the same time, providing there's obviously enough cores. Now, in all of those examples, each consumer sees every event. So you've got multiple threads, and every event is going to those threads, each consumer obviously running in its own thread. There are times when, instead of being single-threaded, you actually want a pool of workers, and you want the event to be processed by one of those workers on a thread, and the other threads can be working on other events. To do that with the disruptor, you can use a worker pool. which is great. It's built in. It says that it's not built into the simple DSL yet. Been working on that the last couple of days. It's pushed up in a branch. Hopefully it'll make the Disruptor 3.0 release. Now, the downside of using a worker pool is that it inherently brings some contention back into the system, because obviously you've got now multiple threads trying to pull the next event, and that's contention. You'll spend time arbitrating that. So it is slower to do it that way, and you need to make sure that if you want to use a worker pool, that you actually get enough benefit from parallelizing those tasks to make up for the cost you will have in getting the data into those threads. The advantage of that approach, though, is that we'll balance across the thread. So if one event takes longer, the other events keep going and pull in more of those events without just getting a backlog on the first thread. But if you do have quite evenly balanced events, so they generally take about the same amount of time as each other, you can do better than the worker pool by doing it yourself. And basically the idea is that instead of having a worker pool, you simply add 3 or 4 consumers, each of which will see every event. But when you create them, you set them up with an ordinal and the number of consumers, and then you check that the sequence number, which you're given, mod the number of consumers equals your ordinal. So in other words, process every 3rd event or every 5th event. And they just work in that round robin. Now, there's no balancing between them. So if every 3rd event is always takes twice as long, then you'll get a backlog on that consumer, and you won't be running at full speed. But it does mean that you remove the contention point, because you've already pre-allocated which events will be processed by which threads just based on the sequence number. Right, so why is it fast? There's quite a lot of detail, as I said. Most of them I've bundled up into what we call mechanical sympathy. And this is a term Martin Thompson uses a lot, and in fact his blog is called Mechanical Sympathy. It's well worth reading. It covers a huge range of ideas and concepts which are built into the Disruptor source code. But the basic idea is that we're running on a certain piece of hardware, and despite the fact that this is a Java library, we should be understanding what's going on underneath, under the covers. So things like making sure we take full advantage of level 1 cache, making sure that we limit our branching, because we know that branch prediction goes wrong sometimes and that can waste cycles. And there's a whole bunch of details like that in terms of understanding the memory model you're working with, and writing code that works best with the CPU that you're running on. And most modern CPUs are very similar in those senses, so it still ports reasonably well. But we run x86, so obviously there's a bit of a bias towards that, but not to the point where it wouldn't run fast on other CPUs either. The two that I want to talk about in more detail today, though, are the batching and single writer principle, because they're things that you can really learn from and use in your own code when you're using the Disruptor to get the most out of it. So let's take a look at batching. The important thing with batching in the Disruptor is that it's a very natural style of batching. It doesn't add extra latency. It will only, if you use it well, it will reduce latency. A lot of people, when they think of batching, think we get the first 10 events and we process them as a batch. But that means that you've got to wait for 10 events to come in before you process anything, so you've increased latency. The Disruptor doesn't work that way. As soon as the first event comes in, it will process that event by itself. But if events pile up while you're processing that event, so now you look back and you say, hey, suddenly there's 5 events there. Now we can process them as a batch. And it does that. The key is really the sequence barrier wait for method. You tell it the sequence number you want to wait for, and it won't return until that's available. But when it does return, it will tell you the maximum sequence that's available without having to check again. So if we look at an example where we've got a consumer currently processing event 1 and the publisher's publishing to event 2, so they're basically in sync at this point. And the consumer, for some reason, takes a long time. So the producer runs ahead and has published into 2, 3, and 4, and is starting to work on 5 before the consumer has finished event 1. The consumer will then call barrier.waitFor2. Tell me when sequence number 2 is ready for me to be processed. And obviously the producer's already published into it, so that will return immediately. And it will return 4, because sequence number 4 is actually ready to be processed. You can go all the way up to there. So without ever calling into barrier.waitFor, the Disruptor will pass you event 2, 3, and 4. And once you finish sequence number 4, it will then process sequence number, it will then wait for 5. So you get this batch of 3 or 4 events all at once. And that's exposed up to your handlers. And it lets you do some clever things to take shortcuts when you're falling behind. So one of the consumers we have off of our ring buffer typically is a journaler. Every event that comes into the system we write to disk because our entire memory model is in RAM, and if you pull the plug, it's gone. But by writing everything to a journal, we know that we've got a record, we can replay it and get our state back. Obviously, writing to disk is pretty slow. We've got ridiculously fast disks, we're doing everything we can, but it's still slower than a completely in-memory auto-matching cycle. And it's the problem point of our system. So we use this batching there to allow it to keep up. And what we do is we simply flush the I/O at the end of a batch. So the code that does that is trivially simple. Each event we get, we write out whatever the data is, and that allows that basically to go and sit in the disk cache or the OS cache, whatever level it actually gets to. And if we're past the end of batch flag is true, we know that there's a possibility that there won't be any more events for a little while. So now is a good time to flush that to disk. So we actually call the flush method. And you can decide whether or not you want to push that all the way through to like an fsync, or whether you just want to try and flush it down to whatever level. But that's a massive win, especially if you are writing in a naive way like this, where we're not trying to fill an entire block on disk, because that obviously, writing half a block causes it to read the whole block, change the bit and write the whole block back. This way, if you fill a whole block with your batch, you just write that one block and it saves you a lot of time. So the other things that we can do with batching is if we're retrieving extra data in, consumers don't have to just be passively reading data off the event. They can actually go and fetch data from other places and add it into the event, and we'll see some of that later. But obviously, if we're doing something like a database call and we get an event in and we say user ID 1, okay, we'll go and get their user details from the database. Okay, user ID 2, we'll go and get their details from the database. It's very wasteful to be doing that back and forth between the database all the time. If we know that we're getting a batch of data, then we just build up the list of account IDs that we want to fetch data for, send them all to the database at once, get all the data back at once, and we save a lot of time that way. And then depending on your application, you can go a step further again and start to suppress some behaviors. So if you're sending notifications each time a value changes, and you get a batch that changes that value 3 times, you may not need to send the 3 notifications. You may only want to send 1. And if it's cheap to identify, you can even skip events. So if you get an event that says create document, followed immediately by an event that says delete document, do nothing. The risk with using some of these things is you are going to pay the price of trying to detect if you can do it a lot. You'll quite often find you get small batches. So if that check is at all expensive, you may find you actually lose more time in the cases where you're keeping up and there is an opportunity to cheat. Then you actually gain when you do start falling behind. So use some profiling, use some common sense, measure it is always the key to any kind of performance. Now the second key technique that really drove a lot of the design of the Disruptor and is probably the most important thing to get right in your code is the single writer principle. Now, Martin Thompson has written about this in great detail, but basically what it says is that one and only one thread may write to any given piece of data. But any thread can read the data. And what it really drives you to do is align your thread model and your data model so that they work together instead of just introducing a lot of contention. A lot of people spend time thinking about their data model, they think about their architecture, but they don't even really register that their software has a thread model. But all software has some kind of thread model. It might be single-threaded. It might be split as many threads as we can. What you really want is a thread model where each thread owns the data it works with and doesn't have to fight to get access to it with other threads. Now, there are times where that's not possible or not sensible. It's not a hard and fast rule, but it does tend to work out really well if you are able to do it. You know, obviously, there's a whole bunch of stuff in the OS where you've got multiple processes firing requests at you, and you probably want to arbitrate them down to one bit of data. you're stuffed. You know, you aren't going to be able to tell those processes to line up nicely and be single-threaded. They're going to come in on multiple threads. You're going to have some contention to order them and sort them through. But in our case, much easier to do things single-threaded in the matching cycle. So we did. And it meant that instead of worrying about locks and instead of writing code that constantly we have to think, oh, could another thread be updating this? Could I be introducing a race condition or a deadlock? We write what we tend to call single-threaded code. And it's a real oxymoron in some senses because there's many servers that the code runs across. There's many threads within each process. It's clearly a multi-threaded system overall. But when you're sitting down and writing code for the LMAX exchange, it really does feel like you're writing a single-threaded application because each thread follows this single writer principle. It owns the data. It doesn't have to contend for access. So we never use the synchronized keyword. It's a pretty dirty word in anything that you want low latency anyway. But we don't have to think about that. We're not worried about, oh, does this need to be a normal hash map or a concurrent hash map? Normal hash map is almost always fine. So if there's one thing that you do, whether you use the disruptor or not, think about your thread model. Get it aligned to the data model. And if at all possible, the single writer principle is a fantastic way of doing that. So let me give you a bit of an example of how that can work and put it into some perspective. So we looked at the pipeline before where we published then A, then B in sequence. Now if we put that on, layer on top some actual actions, this isn't how an exchange actually works, but it's simple. So what we're going to do is we're going to say the order comes into the system, we're going to match it, and depending on how many contracts you match, what you actually bought, there's a certain charge. And so we're going to update your account with that charge. They're the 3 steps. Now I said that this diagram is slightly misleading in terms of it's not passing data from one to the other. They're all sitting in the ring buffer. This is more like what the data flow looks like. So you kind of imagine the sequence barrier, and we're going around clockwise. So publisher first, then consumer A, then consumer B, which in our case is order comes in, then we match, then we update the account. Now, if you remember the single writer principle, we should only be writing from one thread. All 3 things are running in separate threads. And the order is going to come in, and then we're going to add this extra data about what we matched, which seems like a violation of our single writer principle. Suddenly we've got both the publisher and the first consumer adding data into our event. Surely we need some locks, surely there's some contention. It's not actually contention, and it's not actually breaking the single writer principle, because what matters, and this is the mechanical sympathy coming in, is what matters is what the CPU sees. And CPUs don't know anything about objects. They know about memory addresses. And let's ignore OSs rearranging them and being difficult. But essentially, what we want to do is we want to say that a single thread writes to a single memory address. That memory address is owned by that thread. No one else will write to it, but others can read. So in our case, the publisher is going to put into the order field on our object. And then the first consumer is going to set the cost. It's not going to edit the order, and it can't edit the order. That would violate our single writer principle. But it can add extra data into that object, which is then available to our second consumer because it has a barrier. It has this sequence barrier between A and B that guarantees that whatever A does in processing that event will be ready, complete, and seen by B.
Does that mean that you have a constraint where the first part of the order has to be one cache line and the part that includes the cost is another cache line, or are you allowing that? I mean, the thing is that you're going to have multiple writers on a given piece of memory over time, and it's really at a given time, one writer to understand what you're doing correctly. So I'm having a little trouble understanding why you can't write into the ring buffer. You're going to cache miss because the other guy wrote it anyway.
So I'll try and repeat the question for the video. The question was whether each of these data fields has to be in different cache line, because obviously at the CPU level, if we write to the similar memory address that's right beside it, it's going to invalidate the cache line. Yes, cache lines are an issue. One of the things the Disruptor does is actually do cache line padding on its sequence numbers because they're the biggest contended object. We don't tend to worry about it too much for the actual event, but that's predominantly because it's a Java object. So when it's allocated, it tends to be a continuous block of memory, and this is in an array, so it tends to naturally avoid polluting and getting false sharing between cache lines. but also it's in some ways it's because of the fact that the publisher is going to move on. So it's not actually going to read that same event again. You could write to it.
You only have that one. Well, A is the only one that it's right. A is the only one writing at that time.
Yeah, that's true. Yeah, I mean, in that case, you're right. Yeah, it wouldn't be the end of the world if A wrote to the same order.
Other than the fact you want to keep that the same for B to look at.
Yeah. Other than the fact that it would obviously pollute it for B. It's not a concurrency issue. Yes, you could do that. I don't know. Maybe it's kind of, in a sense, just our way that we don't. You're absolutely right. There isn't a strong technical reason not to, if it made sense to.
If the thing is there's more to the world of concurrency. If you have another reason for doing it, that's fine. I'm just trying to feel what the limits are.
Yeah, sure. So if we do look at what this code winds up looking at, I highly recommend using actual getters and setters typically. But just so that you can see there's nothing really up my sleeve, when we're given the event, we just read the order straight out of it. So event.order. It's not a volatile variable. The volatile variable in this sequence is the sequence number, and you update it after you finish processing the event. So I won't go into the great detail of the Java memory model because I don't have that much time. But essentially, because you've seen the previous producer's sequence number update, and that's a volatile. Actually, it's an unsafe. Because you've seen that, you will also have seen everything the publisher has done, including this writing to event.order. So you pay the price for volatile once on the sequence number. You don't have to pay it for all the variables. Similarly, when we want to set the cost to count, yeah, never mind. We just write that to the variable. We don't need to do synchronization around that. Again, it's not a volatile. Now, the other way of looking at it, and a lot of people kind of forget this, they think the disruptor can coordinate consumers. So I should have one ring buffer in my application and consumers for everything, and I set up this great unwieldy set of hierarchy between them. It's not always the sensible way to do it. There's no reason not to use multiple disruptors, and especially if, in the case we were kind of talking about before, if our consumer B didn't need the original order, and we were going to mangle it and write over it, probably better and simpler architecturally to actually just have two ring buffers. So here, this is very much like an actor model, and whether or not you use the full rules of actor models or just this kind of concept, this is bread and butter layout for a disruptor-based application where we have an input ring buffer that actor A reads from, and it writes to an output ring buffer. That might be a straight pipeline. So it might just have input, do some processing, put something different on the output ring buffer. Or in this case, it might be using which output ring buffer it writes to as a way of doing conditional logic and splitting and branching.
So in that case, you have separate namespaces for the different ring buffers?
Yeah, so essentially they're different namespaces.
So they might have the same number, and that's okay because everybody knows which thing they got it from.
Yeah, okay. So one of the key considerations when you do that is whether or not the sequence number is important to you, because obviously you're going to get a different one when you transfer to a separate ring buffer, and whether or not ordering is important. So I'll hopefully look at that as well. The big advantage of doing it this way is that there is no reason that your ring buffers have to all be on the same machine. So the most common model we use is actually that we have a service sitting on a machine, and it's the only service on that machine. So it has some network code that reads off the network, drops the event onto a ring buffer, we process it from there. When we want to send out an event to some other service, it goes onto a ring buffer, and that's picked up, sent over network to wherever that service is. So just like with any other actor model, you have this ability for actors to run either locally on the same machine, possibly in process, possibly in a different process, or be distributed. And it's just a matter of what it is that actually reads from your output ring buffer and what it does with it, whether it puts it straight onto the next actor or whether it sends it across the network, whether it archives it, whatever. Now the choice between one or many disruptors is a really key decision. I said before that your order really matters, and that can affect your choice. But the other thing is, do you actually want every event processed by every consumer? If you don't, if you're going to be skipping events a lot, then there is a cost to that. You're obviously going to make a decision and do nothing. Entirely possible to do with a single ring buffer. You get the event, you just decide not to do anything with it. It's not costing a lot, but you may be better off, in that case, copying only the events that it cares about to its ring buffer. And bearing in mind that that copy probably isn't actually copying the whole data, it's probably copy object reference, so it's not a big copy. The other one, and I think probably the most important one, is deciding whether your events are built up or transformed. So in the example we had before, we're building up the event. The final consumer cares about the original order and the cost. So as we're going around consumers and adding data, the final consumers or the following consumers care about the combination of that data, so building up. If, on the other hand, we were transforming, so string comes in, we reverse it, and we only care about the reversed version, often that's a sign that we want to actually just put it on a different ring buffer. It's a different thing now. It's not building up, and that's particularly why we don't tend to overwrite data that's already there, because it makes more sense for it to be a different event and architecturally move that way. And the final thing is, does order matter? So looking at a few different arrangements, oh good, that came out right on your screen, it doesn't on mine. The simple case is where you have a ring buffer and two consumers reading from it. They're going to see every event and they're going to see them in the original order with the original sequence number. Simple and straightforward. The second one, where we copy from one ring buffer to the other, is slightly more complex, but still preserves order. Assuming your consumer A in that case isn't deliberately reordering things, it's naturally going to pick up an event and put it on that ring buffer. And if it does that with every event, you'll probably get the same sequence numbers, assuming you start at the same place, because every event, one-to-one mapping. But it gives you the flexibility of dropping events. So you decide that's an invalid order, I won't pass it on to B at all. Obviously you'll skip sequence numbers, so they'll get out of sync in that case, but you preserve your original ordering. It's just there's one event missing from it. Similarly, if you decide that this order coming in is actually 3 events for consumer B, you can publish them all to the ring buffer. They will fit in that same logical ordering, but there'll be 3 things there. If you have worker pools, this is where you start to lose ordering. If they're off the same ring buffer, you will preserve ordering. Because consumer B is reading from that same ring buffer, and it's going to simply start at 1, then 2, then 3. That's great in that you know that B is going to process them in the same order. The downside is you've got this pool of threads, and the idea is that if one is slow, the others can run ahead and keep work going. But B won't ever see that. B will wait for that first event because it has to process everything in sequence. So if event 2 takes a long time and is tying up a thread, events 3, 4, and 5 will be ready but won't be accessed by B until 2 is ready. But as soon as 2 is ready, 2, 3, 4, 5 is all there, and so it can process that as a batch. So there is still benefit in having a worker pool, even if you have a sequential consumer afterwards.
What's the downside of having a worker pool be orchestrated by a thread that pulls off the queue and just, and then puts stuff out to it and gets some feedback as to when the guys are done and just sprays it to whoever's ready? And then somebody else can restore the order at the end. Is that a problematic thing? Or?
So what's you're suggesting having a worker pool that effectively sends a bunch of requests. We don't worry about the order for a while. And then once we get the requests finished at the end, then we put them back in order.
Right. In other words, keep adhering to your single writer so they don't contend when you have somebody pass them out to them. Yeah, so they don't contend, yep. That's entirely possible. It's probably not far off this last one where you have a worker pool putting onto a separate ring buffer. If you do care about order, the downside is you have to pay the price of reordering at the end. And again, measure, it may be the fastest way to do it. But in a lot of cases, that reordering at the end winds up consuming a massive amount of time compared to your business logic. Totally dependent on what your business logic is. We have the advantage that our business logic is almost insignificant in terms of the workload we do. So we wouldn't want to deal with sorting. Yeah, so we don't want to deal with the sorting, it would dwarf it. The final case, if you don't care about order, is fantastic. It's basically your best option. Have a worker pool. It's going to go as fast as it can. If one thread gets stuck, the other 2 will keep publishing to the output ring buffer. So your order will change, but consumer B can start processing them straight away. So if order doesn't matter, and a worker pool is a benefit to you instead of just doing it single-threaded,
the two disruptor approach is fantastic for that. And thankfully, I'm getting a time warning just as I reach the end. I really want to encourage you to take a look at the code. I haven't talked a lot about it, and I've talked in terms of concepts a lot of the time. So where I say there's a sequence barrier and it's the same for consumers and producers, it's a little bit of a lie. There's some optimizations you can do for a producer-consumer barrier that means it's actually a separate class. But the concept is certainly the same. So the code is all up on GitHub. We're working on a 3.0 right now, which handles multiple producers in a much more efficient way. Right now, a single producer is fantastic in terms of performance. You can have multiple threads publishing to the same ring buffer, but because obviously that introduces some contention and the algorithm in previous versions wasn't as good, then it slows you down. And so we'll often, in fact, we've been known to take a network hop back to ourselves to get back onto the same thread for the producer just to avoid that contention. Hopefully 3.0 improves that a lot and it goes a lot faster. I've mentioned Martin Thompson and Mike Barker quite a lot. Mike Barker is the current maintainer for Disruptor. Do go and read their blogs, and those blogs have links to the talks I mentioned that cover in a lot more detail the why is this fast and some of the computer science underneath the ideas. So I highly recommend you go and read them. And we might take some questions.
Can you just wait for the mic that you...
Yeah, I've turned out not to be very good at repeating questions. My memory doesn't work well. So you can have a number of threads and they can be set up in a certain sequence. And it gives you some nice happens before semantics so that you know that the event you're processing now, the consumers you've set up beforehand have already processed it. Now at its core, there's just a big ring buffer inside the disruptor, which is our data storage. It's not a particularly new data format. It was invented many years ago, but if you're not familiar with it, a ring buffer is essentially an array that we reuse. So we start at index 0, and whether we're publishing or consuming, we just start with an index of 0 and increment it round. So we go to 1, if we're publishing we'll put in, if we're consuming we'll read out, 2, and so on, until we get round to the last slot. And in this really small ring buffer, that last slot is 7. The next step is we go to 8 and we overwrite 0. So we're going round and round the ring buffer with an except to go single-threaded. So our core matching engine is actually single-threaded, and it goes much, much faster that way. But we wanted to still be able to work in a concurrent fashion and have any of those surrounding jobs, journaling, marshalling, and various other tasks like that, we wanted them to happen on other threads. So we still wound up with this contention point where we're trying to get data from one thread over to the next one into that core single-threaded matching engine. And queues have this issue where they tend to contend on the head of the queue a lot. So we invented the disruptor, and for all of the talks on it and for all the time you can spend talking about it, ultimately all it does is it passes data between threads really, really fast. The second thing it will give you, though, is a way of arranging consumers of that data.
Okay, can I just welcome everybody? This is the first session for today, and actually the first session for the main conference. And on behalf of Linux Australia and LA and the sponsors, I wish you a very pleasant conference. For this first talk, we have Adrian Sutton. He's going to talk about concurrent programming with Disruptor. Adrian is a developer at LMAX, the London Multi-Asset Exchange, writing latency high performance code. And there's a little bit more about him there, but I will let him introduce himself probably better than I can do it. Okay, thanks.
Thanks and welcome. So as Daniel just said, my name's Adrian Sutton and I'm from LMAX Exchange. We're a UK-based financial exchange, and as you can see from the big logo, 3 things we care about are speed, price and reliability. And with exchanges, price and reliability really drive from speed. So a year or 2 ago, we open sourced what is essentially the core of our exchange, which we call the Disruptor. And today I'd really like to take you through that and talk to you about what the Disruptor is, why it's fast, and how can we and you use it most effectively. Unfortunately, it turns out that in a 45-minute talk, there's pretty much no chance of covering all of that. So what we're mostly going to focus on is how to use it most effectively. We will cover what it is and give you a bit of a background because most people won't have heard of it, and we'll learn a bit about the why is it fast. But I would highly recommend you go and look at some of the existing talks that are out there. They've been filmed. People like Mike Barker and Martin Thompson talk about why the Disruptor is fast in great detail. There's kind of hours and hours of content on it that we just can't fit in here. And Trish G does a lot of good stuff on what the Disruptor is and how to get the very basics of it in terms of the code. So the core premise of the Disruptor is that we want to be able to pass data between threads really fast. When we first built the Exchange, we tried it to be multi-threaded and process orders in parallel, and we just found there was this huge amount of contention trying to get the common state of the order book, and there wasn't really much we could do to avoid that.